Today we'll be talking about kinetic molecular theory. So, the postulate of kinetic molecular theory of gases. The first one is that gases are made of tiny particles. Okay, they are so small that we can assume that the size of the gas particles to be negligible in size, meaning that they're essentially zero. We don't need to consider or concern ourselves with the size of the gases because they're so small for the actual particle compared to the space and the volumes that it takes up. Okay. Gas particles are constantly moving around and colliding with each other, with the walls, causing pressure on the walls by colliding with the walls. We've talked about how the more frequently molecules hit a wall, the higher the pressure. So more frequent hitting, the higher the pressure. If it's not hitting the walls as much or as frequently, then the pressure would be lower. Right? Gas particles, we assume, do not repel or attract each other. This isn't always true, but for the most part, the gas particles are going to be zooming around, they bounce off of things, they're not actually attracted to each other, repelling each other in a significant way. And then the average kinetic energy. So kinetic energy, remember that has to do with motion. So the amount of energy is directly related to the motion of the particles. So the average kinetic energy of gas particles is directly proportional to the temperature in Kelvin of the gas. So if you increase the temperature, that will put more energy into our molecules, and our molecules will be moving around much faster. Okay, we'll see the kinetic energy, or the speed at which they're moving around, move around much faster. Go ahead and pause here so the students can finish taking the notes on this, and then we will look at a PhET simulation together. So the sub, if you'll please just push pause and let them copy this down. When they're done, go ahead and push play again, and we will keep playing. Okay. So hopefully you're feeling better with the postulate of kinetic molecular theory. So let's actually look at it using this PhET. Okay, so in here we have a gas inside of this box. Well, I guess technically we don't yet. So we can pump molecules. So there's our gas molecules into the box. You can see that the pressure now has gone up a little bit as the particles are moving around and hitting the walls. You can see that they're ricocheting off walls, off of each other. They're not really staying, they're not staying put by any means, and they're not really attracting or repelling each other. Okay, we're going to look at a few different things. Is the temperature and the pressure stay constant? And this is like what we did in the lab. If we were to decrease the volume, we'll see that the molecules are hitting the wall more frequently, increasing the pressure. Similarly, so currently if you look at the pressure, it's currently at about, I don't know, 18-ish atmospheres. If I then expand my volume, you'll see that the molecules are still moving around at the same speed, right? But there's a lot more space, and so they're colliding with the walls less frequently, decreasing the pressure to 8-ish. Okay, so if you increase the pressure, or sorry, if you increase the volume, the pressure decreases. Similarly, as you decrease the volume, the pressure increases. All right, now let's look at pressure and molecules staying constant. Let's see, hold on. Let's do hold constant pressure. Okay, if I were to increase the heat, okay, so let's decrease the heat. We're going to cool it off. Okay, as it cools, oh, dang it. I want, why is this not working? There you go. As we cool it, you'll see the molecules start moving less, they're not moving as fast. They're colliding with the walls less frequently, so the overall volume decreases. This is what you would see in, say, a balloon. If you were to take a balloon from inside, you take it outside into the cold weather, you'll see that it decreases. It's because the particles are hitting the wall less frequently because they're moving around slower. If you increase the heat, you'll see that the particles start to move around faster. And I went a little too far. They move around faster, they're colliding with the walls more frequently. If we're keeping pressure the same, then the volume will increase. Okay. So now if we keep the volume the same, so let's just, set it about there. And we'll keep the number of molecules the same. And we increase the heat, you'll see that the heat, you'll start seeing the molecules speeding up. Okay, as the molecules speed up, they start colliding with the walls more frequently. You can see the pressure gauge is going up and up and up and up, and you see those molecules speeding up. Okay, if you go up high enough, we can blow the top off. So let's see, go up high enough. Boom! Oh my gosh, it blew up. All right, anyway, all right, so you can see those molecules are moving around much faster now that it's hotter. Similarly, if you cool it down, you can see the pressure is decreasing because they're hitting the walls less frequently, making for a lower pressure. All right, and then let's look at if we increase the number of molecules. So if I increase the number of particles I have in here, look at what's happening to that pressure. That pressure is going up and up and up and up. And if you think about it, there's a lot more molecules in here. They're going to be hitting the wall much more frequently, increasing that pressure. The other thing that I want to look at, let's just reset this real quick. I'm going to put some of those larger molecules in there, and then I'm going to put some smaller molecules in there. So something you'll notice with the smaller molecules is they're actually moving faster. But temperature is directly related to the energy, the kinetic energy of these molecules. But if you think about larger molecules, it's going to take more energy to move something larger than it does something smaller. And so the smaller gas molecules are going to be moving around a lot faster because it takes less energy. Their energy can go fully into kinetic energy so they're going to look and move faster. The larger particles, it still has the same amount of energy, but they're not going to be moving as fast because they have a larger mass. Regardless of them being two different gas molecules, you'll see that they do not interact. We assume that they are not repelling nor attracting each other. You can see that going on here. Of course, that's not always the case, but that's what we can safely assume because majority of the time, gases do behave more or less that way. All right, so let's look at some conclusions together for this, okay? So the variables that are directly related are volume and temperature. So if volume goes up and if temperature goes up, volume goes up. If temperature goes down, volume goes down. All right, pressure and temperature. As you increase the temperature, the pressure will go up. As you decrease the temperature, the pressure will go down. And moles in pressure. If you increase the number of particles, the pressure will increase. If you decrease the number of particles, the pressure will decrease. The indirectly related variables within the ideal gas law are volume and pressure. So as you increase the volume, the pressure decreases. As you decrease the volume, the pressure increases. And then additional conclusions that we have for this is that the ideal gas law, it's a really good way to assume most gases behave, but it does have assumptions. So the ideal gas law assumes that the particles are negligible in size, meaning that they are super, super tiny. I know the PhET showed them so that way you can visually see the size of them. But those sizes, when compared to the amount of space that they're taking up, is negligible. They are tiny. The PhET had them as bigger so that way you can actually see them. Otherwise, it would well, be a very silly, it's nice to be able to see it, right? It wouldn't be a very good simulation if you couldn't see the particles moving around. Um, then the pressure is caused by molecules colliding with the walls. So the more frequently they collide, the higher the pressure. The less frequently they collide, the lower the pressure. And that the ideal gas law assumes that gas particles do not repel or attract one another. Okay, this is a fair assumption because for the most part, there's not a whole lot of intermolecular forces going on when in the gas phase. So that is all I'm going to talk about for the kinetic molecular theory. Thank you for your time.